Good day, everyone, and welcome again to our webinar presentation. My name is Adam Harris, Managing Director here at C-Therm Technologies. Very pleased to welcome you to today's webinar presentation. We're hosting these weekly now. They're application-focused presentations designed to provide an educational benefit in highlighting different published works and different application data that's been curated by one of our specialists. So Sarah Ackerman, who's with me here in studio, is going to be leading today's session. She's been doing a fantastic job curating these weekly. Last week we had a wonderful webinar on battery thermal management. If you're interested in some of those previous recorded webinars, I'll ask my colleague Rosa to just drop in a link on the chat box just to where you can view some of those previous recordings. They're free to access. There's a wealth of knowledge kind of packaged in there. You can fast forward if there's a section that you want to jump over. It makes it a really great resource to have a look at some of the different work being done in different areas of application related to thermal conductivity. So today's session should run for about 1 hour. We are recording the event, and we will similarly be posting this file up as a recording. It should be online within 24 hours, and you will receive a link automatically if you've registered for this webinar to the recording. We'll also send a follow-up email that will provide links to some of the published resources that we're going to be referencing in today's webinar. It's important just to note that we do not own the copyright to these publications. We're taking small samples from them and offering a short highlight on some of the work. But if you'd like to obtain a full copy of the publication, we'll provide you a link to where that can be purchased. At the end of this webinar presentation, we'll stop the recording and we'll unmute the line, and there will be a great opportunity for a Q&A session is moderated through the chat box. As we go through the content, if there's anything that really attracts your attention, you'd like us to dive into deeper, please flag it in the chat box. We'll either attempt to address it in real time or we'll come back to it in the Q&A session itself. So just before I pass this over to Sarah, I'm going to provide a little bit of background information on who C-Therm Technologies is, and I'm just going to give a real quick overview of the product capabilities that exist that are featured in this educational webinar that is application focused on nanocomposites. Nanocomposites is, I would say, the most popular application for the instrument. Polymers and nanocomposites, which really go together, is the single largest application use or field of use for our instrumentation. So it's near and dear to our hearts and one we know very well. We have on the participant list a wide range of folks joining today. We have partners from all over the world, with clients from all over the world. I want to welcome you and really say how much we appreciate this opportunity to connect with you. We know that in the current global situation, the pandemic, COVID-19, many of you are having to balance parental responsibilities, childcare, along with a full-time job that hasn't stopped. If anything, it's probably more demanding now than ever. And so just really want to recognize and appreciate you taking the time to join us for this webinar. In looking at the registry, I see some names that are very familiar. I also see some folks that may be newer to C-Therm Technologies. So I just wanted to take a quick opportunity to explain a little bit who C-Therm Technologies is. We're really niche specialists in thermal conductivity specifically. So we're not a thermal analysis group that offers a broad range of products and instrumentation. What we do is we have a laser-like focus on the area of thermal conductivity, and particularly driving innovation in the area of thermal conductivity characterization and focusing on the transient-based methods for thermal conductivity. We've developed and patented some of our own methods, such as the modified transient plane source technique, and then we've also advanced considerably other commercial methods that are based on ASTM and ISO methods. And really what we try to do in life, our raison d'etre, is to simplify thermal conductivity measurement, make it more accessible, and ultimately try to make it easier to get property data on your materials. It's really representative for the application you're intending to use it. And that means sometimes operating in different types of environments. Could be high pressure, could be a radiated environment like a hot box in the nuclear industry, could be high humidity, elevated temperatures. Our sensors are all external by design to give you that maximum flexibility. We've developed some specialized accessories to support this. Of particular note would be our range of high pressure cells. We're the only commercial group offering a high pressure cell for thermal conductivity. Just speaks to some of the different types of environments which we can operate in. And what we strive to do is to make that easier and easier for you to get representative data for your material. If you look at what impacts the effective thermal conductivity of the material, pressure, humidity, temperature, all of these things have an impact on the conductivity. So what's really important is that you get truly representative data for your material and field of use. So this slide just gives you a quick lineup of our products. Today we'll be highlighting the Trident thermal conductivity instrument. This is the pyramid-shaped product in the middle. You can see that in front of it are three different types of sensors, which complement each other's in terms of their use. So the cylindrical stainless steel object, that's the MTPS sensor. It's a single-sided sensor. It's the simplest to operate, the most sensitive. It's typically the go-to sensor across the broadest range of conditions. That's solids, liquids, powders, paste. You'll certainly see it highlighted quite a bit in the content that Sarah has curated. The needle object there is a transient line source sensor. It's our most robust sensor. It's sheathed in stainless steel. It's really meant more for semi-solids and samples that may bond or cure to the sensor and risk damaging the other sensors. So it's very complementary in that respect. It's great for polymer melts, also commonly used on soils and other types of semi-solid materials. I don't suspect you'll see a whole lot of it in this presentation. It's really more meant for polymer melts in these types of situations. That said, the third sensor is very interesting and really provides some advanced capabilities, and that's the hot disk style transient plane source sensor. The end of that nickel foil that's encapsulated in the yellowish polyimide is a disc shape, and that is sandwiched in between two samples. And this is a very complementary method to the MTPS technique, which is simple, easy to use, very accurate, but a bit more boxed in terms of the experimental parameters. In contrast, the TPS method gives you full control. It is designed and oriented to a more experienced user. So you are given full control over the timing, the power parameters. There's different size sensors available. You run the regression analysis, which is automated on the MTPS. And this gives you a lot more capabilities to test under more challenging type of scenarios. There are some specialty utilities in particular, which will be referenced in this presentation. So testing thin films, testing anisotropic material and the X and Y plane. And it also gives you an ability to look at slab samples, which are thinner samples. So the TPS is a great complement to the MTPS, and you'll see both well referenced in this presentation. The product to the right is the TX Touch Experience platform. This is really more oriented towards characterizing touch from the perspective of warm feel or cool touch. Very important characteristic in consumer goods, in textiles, sporting apparel. We have a webinar next week on this area of application, where we'll be bringing in a researcher from the University of Oregon. Susan's group there will be presenting on how they're working with Leading brands around the world, including groups like Under Armour, Columbia, and others in really indexing that performance and developing product segmentation based on the performance of thermal touch. So some pretty cool stuff there if you are in that space. The other product on the far left, I'll just reference in passing. This is the thermal conductivity kit. It's a very low cost offering in contrast to Trident, which is a research grade instrument. The TC kit is very much an entry level. It's oriented from a price point perspective towards hobbyists. So if you're a startup working out of a garage, you're just looking to get into the game of measuring conductivity, this is a great place to start. You pair it with a Keithley source measure unit and a laptop, and you've got everything you need to run a conductivity of a solid sample up to about 65 watts per meter Kelvin. It comes with the software for data acquisition and the regression analysis. It comes with a reference material and, of course, the sensor itself, as well as instruction sets. It's also employed in different academic labs for teaching concepts of heat transfer. There are some drafted exercises, lab exercises that you can take your students through and use this as a teaching tool as well. But it does do a very good job of generating conductivity data under more basic conditions and is offered at a very attractive price point. That's offered on the Shopify network. Rose, I'll ask you to drop in a link to where you can find out more information about the TC kit for anyone that's interested, please. So with Trident, this is really about bringing multiple different capabilities together. When we talk about thermal conductivity, and particularly nanocomposites, we're often dealing with a broad range of scenarios in terms of sample formats. You've got thin films, you've got anisotropic samples, you might have thicker or thinner, different geometries. And so there's not a universal silver bullet out there in terms of a method that deals well with all of those scenarios. So what we've done, and philosophically we feel very strongly about when it comes to measuring conductivity, is really about having a toolbox available that has a variety of options available to help characterize your needs today and also those future needs that you may not be able to fully envision from next year. So with Trident, it's one instrument, but it's three different methods all packaged together in one platform. That, in our philosophy, is it's better to have options. So you have MTPS, which is the guard ring technology. You have needle, a transient line source, and the flex transient plane source, all available with that same platform. It is modular, so if you don't need all of those capabilities, you can configure the product at a reduced price point and rolling back the ultimate configuration. But it also future-proofs you for, if you ever need to add the capabilities in the future, it's easy to do so. You don't have to buy a whole new instrument to add those capabilities. This is just giving you an indication of the size of the sensors, and this helps inform the minimum sample requirements. So the needle is quite long. It's 150 millimeters in length. It's the largest sample requirement of our methods. And again, it's meant for more semi-solids, polymer melts, these types of scenarios. The TPS in the middle is available in different size formats. So the standard ones are 6, 13, and 30 millimeters in size. Those are diameters. This is sandwiched between two homogeneous samples. So you would take your sensor and you would sandwich it in between two samples. And then you have the MTPS sensor on the left. This is it's a single-sided sensor. The active area of the sensor is 18 millimeters in diameter. You'll see other groups advertise a single-sided capability, but what they lack is what we described as a guard ring technology. And this is a patented innovation by C-Therm Technologies. So there's actually two circuits in that sensor. There's the main sensor coil, which is the active sensor, and then there's also a heated ring that goes around it. And that's to ensure that you get a one-dimensional heat flow into the sample material. This is very important from the perspective of measuring the effusivity and conductivity of the material accurately in employing a single-sided sensor. Why is a single-sided sensor interesting or novel? If you think about sample formats, this gives you a lot more flexibility because all you have to do is find one good contact point on the sample material itself. We have a client in the UK that works with conductive polymers, filled polymers. And one of the things they find really helpful to do is to actually map some of the different regions of a manufactured piece to better understand how well the additive is being distributed, because so often when we're talking about nanocomposites or filled polymers, the challenges of achieving a higher effective thermal conductivity are often related to the challenges of achieving a good distribution of that additive material, whether that be glass fiber, boron nitride, carbon nanotubes, whatever you're using to help improve the heat dissipation. Achieving good uniformity is often a critical performance aspect for ultimate success. Rosa, I'll just ask for you to drop in a link to some of the testimonials that we have. I know there's, I think there's about 30 or 40 different testimonials available on the page. If you're interested in better understanding what our typical customer experience is like, there's a great list here available of what our clients experience, what their thoughts are on the equipment. And I believe there is some reference to that thermal mapping in one of those testimonials. Okay, at this point, I want to pass it over to the star of the show. Sarah Ackerman is the lab manager at Thermal Analysis Labs, a division of C-Therm Technologies. Sarah is an expert in thermal conductivity characterization as well as broader thermal analysis. She loves helping clients address challenging thermal characterization issues. We're doing a lot of contract testing and supporting groups that are restricted from their labs. C-Therm is open and we are at full capacity in terms of our analytical lab. We have TGA, DSC, dilatometry, thermal conductivity. All of these techniques available as a service. And I'm sure Sarah would be happy to talk to you about that. But today, we're focused on looking at thermal composites, nanocomposites, and the characterization of thermal conductivity as a critical performance attribute. So I'll pass this over to Sarah at this point, and I'll rejoin you guys in the Q&A session at the end of Sarah's curated presentation. Sarah, just a note, I think you're muted.
I am, thank you. So thanks again for the introduction, and thanks for notifying me that I'm muted. I'm using a new mic today, so just getting used to the new sound system. Moving in, so we'll start by discussing what nanomaterials actually are. So Wikipedia actually has a very good definition of nanomaterials, but in summary, they're basically materials that are very small and have typically a size of between 1 and 100 nanometers. So because they are so small, they behave in ways that are oftentimes quite different from how you might normally expect a bulk material to behave. So as an example, one would typically think of something like a plastic material, like a polyethylene material, as having a quite low thermal conductivity. You'd expect it to be fairly thermally insulative. However, a single strand of a polyethylene molecule, rather, actually has a fairly high thermal conductivity along the chain. It's only when you get it into a bulk sample, the heat transfer between different polyethylene molecules becomes an issue that you'll notice the thermal conductivity decrease substantially. So, a lot of the times when you're looking at these very small materials, you can pick certain ones that have similarly high thermal conductivities, even in bulk thermal properties, and use them as fillers to help improve the thermal conductivity of a composite material. A few of the common materials used for this purpose include things like graphene, which is basically single sheets of graphite. Um, Carbon nanotubes, including single carbon nanotubes and also carbon nanotube assemblies, and somewhere between the two is would fall the multi-walled carbon nanotubes. Diamond dust is used in some highly specialized applications. Of course, graphite is very popular. And on the lower end, on the more cost effective end as well, you can run into more ordinary materials that most people would be quite familiar with, including copper and aluminum. And we just have stainless steel there for reference as another common material that most people would be familiar with. And stainless steel is actually more thermally conductive than most non-metals out there, and actually even more thermally conductive than a substantial number of metals. But its thermal conductivity is around about, depending on the grade, between about 11 to 20 watts per meter Kelvin. And as you can see on this chart, that's low enough that it doesn't even really register on the chart. So nanomaterials are typically used aside from a few very specialized sorts of applications, they're typically used in the making of composite materials, where these nanocomposites are used sometimes to provide improved structural support while saving on weight. And at other times to aid in thermal management. We'll be focusing mainly on the thermal management nanocomposites out there for the simple reason that that's the application that's relevant to the content that we wanted to present today. Um, but a lot of the time, these nanocomposites you can kind of serve two different purposes. A lot of the time, as you improve the thermal conductivity, you also improve things like strength, mechanical strength. So a lot of the time, you're serving both ends at the same time. They can be used in places like aviation, where many of the parts that used to be made of metal are now being made of carbon composites to save on weight while maintaining structural integrity. They're used in electronics to help provide structural support while also aiding in heat transfer of the electronic components. They're used to make more thermally tailored concretes and mortars in construction. They can be used in the automotive industry in a wide variety of areas, ranging from engine components to the automotive interior, and in some cases, it also includes some of the structural parts of the vehicle. Um, Nano composites can also be used in industrial settings where they're primarily typically used to aid in heat transfer to replace parts that would normally be made of polymers, and aim for something that's going to be a bit more thermally conductive to help with the thermal management. They can also be used in things like the grips on a power tool, or the outer casing of power tools. Again, it's mainly to aid in the structural integrity in this case, but in some cases, it's also to help with the thermal management of the tool. It's used in aviation. Many of the the parts in a rocket that need to be light but also quite strong, and in some cases also have a high thermal conductivity, are made out of nanocomposites. And finally, they're seeing increasing application in things like cold chain technologies, although in that case, the aim is typically actually to reduce the thermal conductivity, and they might include things like nanoparticles of aerogel type materials into the composite to kind of help preserve the food that you're transferring at a lower temperature. So I've spoken about these applications and how thermal conductivity can be important to them, but we should probably define what thermal conductivity is. For most of you, this will be review, but if it's new content, thermal conductivity is basically the rate at which heat can flow through a known cross section of material. Um, Subject to a known thermal gradient or temperature difference. So if you have one side of this red block here that is maybe at your household interior temperature, 20 degrees Celsius, and maybe it's a winter day up here in Canada, it can be minus 35 Celsius. So let's say the outer wall is at minus 35 Celsius. The thermal conductivity or the effective thermal conductivity of the wall would be what governs how much heat your house loses to the outside environment, and therefore how much of your energy bill that month goes to heating. So that's kind of a more common application for thermal conductivity that most people interact with. Everybody's had the experience once or twice of sitting next to a drafty window in the middle of winter, or maybe sitting right next to a drafty wall in a hot summer day when you really want your air conditioning to work, and been a bit of had the experience of being a bit uncomfortable as a result of poor heat transfer. So that kind of gives you a image of how thermal management can be important. Um, so looking at nanocomposites, we should probably talk about what governs the thermal performance of these composite materials. The first one is pretty obvious and it's pretty intuitive. Filler load. So how much of these nanoparticles that are either increase or decrease the thermal conductivity are you putting into the polymer material? Generally, more is going to be better. The more particles you add, generally that will be associated with a better improvement in the thermal performance, either a higher or lower thermal conductivity. But sometimes you can run into other issues if you put too much carbon nanotubes into a carbon composite, for example. It might become too rigid for your application. And too brittle. So there's always a little bit of a balancing act between the thermal properties and some of the other mechanical properties that you might be interested in. The second part of the factors that govern thermal performance is how well organized your filler particles are. So on the right hand side, you can see a little drawing I did up that basically describes how the fillers actually work in a composite material. So I've chosen, for the sake of easy drawing, I've chosen a filler material with a relatively large aspect ratio, which I'll get into next. But basically what you're trying to do when you add a filler to a nanocomposite, and then your goal is to improve the thermal conductivity, let's say, what you're trying to do is provide a pathway for efficient heat transfer. And so obviously the more filler you have into the nanocomposite, the more opportunity your filler has to make contact with other filler particles and provide that pathway for the efficient heat transfer. But also, if your fillers are relatively more organized, if they're aligned in a single direction, for example, you're going to have more opportunity for that better performance because the end of one will be probably pretty close to the start of another one. And now, more recently, they've been looking into the effective aspect ratio. An aspect ratio kind of goes hand in hand with the filler organization, where if you have a filler that's long and thin and you organize it, you have more of a pathway for more efficient heat transfer before it has to cross the resistance of the matrix, which is usually a polymer. Most polymers have thermal conductivities around about zero point 0.2 to maybe zero point 0.6 watt per meter Kelvin. If you're making composite with a glass instead, like a borosilicate glass, that might go up to about 1, maybe 1.5 watt per meter Kelvin. But regardless, your matrix material, if you're trying to make a composite that will increase the thermal conductivity, your matrix material is always going to have a much lower thermal conductivity than your filler. So the less the fewer number of times that a heat phonon has to propagate through the matrix instead of through the filler, the higher your effective thermal conductivity is going to be. So now that we've kind of covered the general idea of these nanocomposites in at a very high level, we'll get into some application data. This first one paper is from Nanoscale Research Letters. It's titled "Great Thermal Conductivity Enhancement of Silicone Composite with Ultra Long Copper Nanowires." So again, in this one, they're looking at using copper as a filler, which copper has a fairly high thermal conductivity, around 400 watt per meter Kelvin. And they're looking to use, obviously from the title, they're looking to use the length and the long aspect ratio to help improve the thermal conductivity. So you can see on this slide some scanning electron microscopy of the three different nanomaterials that were made. Um, and so they did compare the copper nanowires with graphite nanoplatelets, or GNP, with the performance of multi-walled carbon nanotubes, which is abbreviated by MWCNTs. So you can see the similarity in terms of the superficial appearance between the copper nanowires and the multi-walled carbon nanotubes. The graphite nanoplatelets are more two-dimensional heat transfer materials, so they do act as a good filler material. However, um, they do act as a good filler material, but their filler action is two-dimensional. So instead of only being able to really efficiently transmit heat along the axis of the tube, they can transmit heat in the plane of the platelet. So this slide shows the comparison of those three different materials in terms of the thermal conductivity enhancement relative to the neat polymer as a function of the volume fraction of filler added. And by choosing very high aspect ratio copper filler of these copper nanowires, you can actually exceed the thermal performance of the graphite nanoplatelets and the multi-walled carbon nanotubes, despite the fact that graphite nanoplatelets and multi-walled carbon nanotubes have a much higher, probably at least 2 to 3x higher thermal conductivity than the carbon or the copper does. So this just shows the importance of the. I apologize for that. This just shows the importance of the choice of aspect ratio and the engineering of the aspect ratio with the filler in terms of the performance of the nano composite. This slide also shows the thermal. This shows similar data, but looking instead at the thermal conductivity instead of the relative thermal conductivity enhancement. And it also shows some straight line plots that were generated based on models using effective aspect ratios of 100, 200, and 350. So you can see how the copper nanowires, because they have such a high aspect ratio, uh, a each incremental addition of copper nanowires improves the effective thermal conductivity much more so than the addition of an incremental addition of a multi-walled carbon nanotube. This next paper that we're looking at is called Massive Enhancement in the Thermal Conductivity of Polymer Composites by Trapping Graphene at the Interface of a Polymer Blend. So in this paper, they're looking at affecting the filler organization part of those three factors I was discussing earlier. So basically, the idea here is when you're making a polymer blend, you'll have regions that are relatively more rich in one type of polymer and other regions that are more rich in the other type of polymer. And at the interface, if you can trap the filler particle there, you will have a built-in organized network for heat transfer. So this slide looks at or describes the principle of what they're doing. So what they were looking to do was generate these thermally conductive polymer composites by trapping the graphene at the interface between the polylactic acid, which is abbreviated by PLA in these images, and the ternary poly epsilon caprolactone, which is the copolymer for this polymer blend. And so the idea is if you can trap it there, you'll get a better and more organized uh, heat transfer network. So in this shows the results of their work compared with nanocomposites generated using the graphene and each component part of the polymer blend. So it just shows that trapping the graphene at the interface of the polymer blend really improves the organization of the heat transfer network and therefore improves the overall heat transfer efficiency. So this work was generated using the C-Therm MTPS sensor, which enabled testing of single pieces of the polymer composite materials. The next slide is entitled Synergistic Improvement of Thermal Transport Properties for Thermoplastic Composites Containing Mixed Alumina and Graphene Fillers. Again, it's also out of the Donghua University. So the idea in this case, and like with many polymer composite papers, the real driver behind this work is the fact that as modern electronics increase in power, but there's increasing focus on bringing the weight of those electronics down. Um, that is going to generate an issue where if you're generating all this waste heat from the electronics function and the batteries, how do you get rid of the waste heat? And if you're trying to minimize the weight, you can't necessarily use traditional heat sink materials like aluminum and copper because they add a fair amount of mass to the device that you're looking to engineer. So has been what this has driven largely is the design and engineering of parts that were traditionally purely there for structural support to also pose a heat transfer role. So, for example, designing a thermally conductive dielectric material that can act as your circuit board, but also aid in the heat management of the overall system. So, this slide shows the result for each of the component parts. Um, Looking at the performance of the filler materials separately. So the thermal conductivity enhancement for alumina has a bit of a non-linear behavior, and that's largely because the alumina is much higher thermal conductivity than the bulk polymer. So when you start to get uh, or when you start to get to a very high weight percent loading, in this case upwards of 80%, the contact resistances become uh, increasingly less significant for each increment of mass addition. So you'll get much more efficient heat transfer in something that's like 80 or 90% alumina than something that is only 10% alumina when you're dealing with a matrix that's thermally insulative. Graphene, on the other hand, also has a very high or also has the effect of improving the thermal conductivity, but it's quite a bit more efficient. So you can achieve about 100% improvement in the thermal performance of a filler material with the graphene additive. In only adding about 5 mass% of graphene, compared to the alumina, to achieve the same doubling of the thermal performance, you have to add almost 70 weight percent of graphene, or of the alumina rather, to achieve the same performance as the graphene. Again, these data were collected using the modified transient plane source technique, which is offered on our Trident unit. And this characterizes or basically compares, if you're mixing graphene with alumina as fillers, how do they perform compared to a single filler material? And you can see the red um, part of the bars on this chart is basically the extra performance. So it's performance that would not be there except for because of synergistic interactions between the alumina and the graphene. And again, this data was collected using the modified transient plane source technique available on Trident. This next set of data is entitled Boron Nitride Nanosheet Enhanced with Cellulose Nanofiber Aerogel with Excellent Thermal Management Properties. So, this is kind of taking the principle of making a lightweight, thermally conductive backbone to the extreme by making the backbone out of an aerogel. So, aerogels, of course, are 3D networks that are over 98% air by mass. So traditionally, these are extremely thermally insulative materials. They're the only known materials that offer a thermal conductivity of less than that of air. However, uh, recently there's been a view to see if you could keep the mass benefits of the aerogel material, but make them more thermally conductive. So you can use them. Aerogels also have the benefit of being very structurally strong relative to their mass. So you can use them in theory as structural support. Um, but that poses the problem because they are, of course, extremely thermally insulative, generally speaking. So if you want to be able to manage the heat properly and move that heat away from where it's being generated, an aerogel that manufactured with traditional methods will pose a big challenge to that goal. So this work is aimed at generating an aerogel that's not extremely thermally insulating. So this slide basically shows the concept of how these aerogels were manufactured. It's essentially a four-step process where they first prepare the nanofibers and also exfoliate boron nitride to generate boron nitride nanosheets, and then basically make that into an aerogel material using a sol gel process. And so four different aerogels were designed. One is using pure cellulose nanofiber. The next would be using a silylated cellulose nanofiber. The third one is a composite of the carbon nanofiber with the boron nitride nanosheets. And the fourth is a silylated uh, cellulose nanofiber composite with the boron nitride nanosheets. So you can see there's a six-fold improvement in the thermal conductivity of the silylated cellulose nanofiber material. That is a composite, of course, with the boron nitride nanosheets. So, from this work, the authors were able to conclude that these boron nitride nanosheets provide a substantial thermal conductivity improvement over the cellulose nanofiber gel materials, and therefore they're promising for application in and other systems where you need a very lightweight structural support, but you also need to be able to move heat away from where it's being generated. Uh, the next set is titled Synergistic Effect of Micro Bamboo Filler and Graphene Nanoplate Mechanical Properties of Epoxy Based Hybrid Composite. So this is looking at an epoxy nanocomposite where bamboo and graphene were used as fillers. Bamboo is often used as a kind of more renewable source of fibers to add to polymer composites to improve the structural strength of the polymer composites. And of course, the graphene fillers are often used to improve the thermal conductivity of these materials. Um, Interestingly, I included the SEM images in this presentation because you can see in the SEM as you increase the fill percentage, you can see a formation of clusters in the composite, and that does have an implication for the overall efficiency. If you've got pockets of very high filler concentration and other pockets of very low filler concentration, that can serve to decrease the overall efficiency of the heat transfer. And when they look at the thermal conductivity results as a function of the bamboo filler weight percentage, you can see that those clusters that we noted on the SEM images do seem to be decreasing the overall efficiency of the heat transfer. Up to 5 weight% loading, however, the addition of bamboo does improve the thermal uh, conductivity of the composite material. So this data was collected using the modified transient plane source method, or MTPS method. Again, this method is available on Trident, and it's very popular for this kind of R&D work because you only require a single specimen, and the test can be conducted in a single-sided manner. The next set of application data is called size, concentration, and content effect of copper graphite hybrid dopant on mechanical thermal and electrical conductivity characteristics of unsaturated polymer resin. So this was published in Acta Physica Polonica. So the idea here is that they have this unsaturated polymer resin matrix, and they're looking at two different filler materials and looking to see, do the fillers improve things on their own? Do they improve um, and if they do improve it on their own, do they improve it more if they add both types of filler? And you can see some effect on the right hand side, looking at the thermal effusivity, as one-dimensional heat transfer is actually very important to the end use goal for these researchers. They intended to use this in an electronic device that where the heat transfer would be approximately one-dimensional. So the effusivity in this case was a key performance attribute. They also looked at the thermal conductivity enhancements of the different types of um, nanoparticles on uh, the base polymer. So on the left-hand side here, you can see the thermal conductivity enhancement of the copper graphite polymer composite as a function of the average filler particle size in micrometer. And so this can go to the filler organization and the filler aspect ratio effects on thermal conductivity enhancement. You would expect to see this sort of a relationship between the average particle size and the thermal conductivity. On the right-hand side of the slide, you can see where they've charted the thermal conductivity enhancement of two different types of composites and compared them with different thermal models to determine what type of model is best suited to reproduce these effects in a computer simulation. Now we'll kind of take a sideways step. So all of the data up until now was generated using the modified transient plane source method. We're going to highlight some data using the transient plane source method's anisotropic utility from Trident. So the anisotropic utility is basically designed, and you can see in the lower right of this slide, we've drawn a symbol of a cylinder. So what it's designed to do is look at what is, if you think of it as like radial or plane in the plane of the disk, the thermal conductivity in that plane, and also the thermal conductivity through the plane or axial to the cylinder. Um, and you can measure both of these at the same time with this utility if you have knowledge of the heat capacity and the density of the material. So, anisotropic materials, in short, they're basically materials that have direction dependent properties. Next of this talk, we'll be focusing on thermally anisotropic materials because something can be anisotropic with regard to one property, but isotropic with regard to another different property. It's a bit uncommon, but it does happen. So in this case, we're looking at a material that, if you think of a cube, for example, we'd be considering a cube where the C-axis would have a different thermal conductivity from that of the B-axis and the A-axis. But the B and A axes have the same thermal conductivity in this case. So this is some test results looking at anisotropic polymers, looking at Lexan, polymethyl methacrylate, and of course, and finally, garolite G10, comparing the expected thermal conductivity provided by the supplier versus the measured thermal conductivity. This next application is looking at the thin films utility. So looking at characterizing thermal conductivity of thin film type materials. A lot of these developing polymer composite and nanocomposite materials are intended for use in thin film applications, and oftentimes the thermal conductivity of a film might not be exactly the same as the thermal conductivity of the bulk material. So, when you're looking at a thin film material, you want the sample to be ideally the same diameter as the sensor, and the thickness can range from about 0.05 millimeters up to about 5 millimeters. The minimum thickness is going to depend on the thermal conductivity of the material because the minimum thickness is dictated by the thermal resistance of the sample material. So, um, by varying the number of films, so when you're doing a measurement on this, you take a measurement with no film on the surface, and then you can add one or more layers of thick film material. And so by doing this, you can determine the effect of the film, but also the effect of the contact resistance of the film. So this is an example of this kind of test. So you take the measurement with no film attached, and then maybe one layer, two layer, or three layers, and the slope of that line would give you the thermal conductivity of the thin film material. Of course, you can also conduct a measurement with only a single thickness. It's just the having extra data in your straight line approximation gives you a better degree of confidence in the fit of the straight line. And this is a collection of thin films data that we've collected with our thin film utility on Trident, looking at Nomax, Kapton, HN, Mylar, polypropylene, and cellulose acetate thin film materials. Um, so that wraps up my contact for today. So at this point, I'm going to turn things over to Adam, who will talk us through some upcoming webinars and also probably open up the Q&A session. I think you're on mute, Adam. No. I think you're still muted, Adam.
Okay, I'm hoping
There we
that
go.
resolved it. Okay,
Yes, it did.
apologies, everyone. Just a little technical hiccup there. Sarah, great job. Great overview on nanocomposites. As I mentioned in the beginning, it's one of our most popular applications. We see a wide field of use with Trident, everything from ceramics, phase change materials, explosives, batteries, etc. But nanocomposites and all the different areas that they're applied. And I think Sarah provided a great context for the different application field uses for nanocomposites. Certainly make it our most popular application. So wonderful job there, Sarah. As you see on screen, we've got another webinar scheduled next week. It's on the testing of textiles, looking at how thermal effusivity is used in claims validation. We'll be having a researcher from the University of Oregon that's coordinating a project with major sports apparel brands such as Columbia and Under Armour, presenting some of the data generated and the work done to date in generating different thermal spectrums or performance ranges in terms of product performance as it relates to cool touch or warm feel. With the warmer summer here we're experiencing now in Atlantic, Canada, one of the topics is going to be on, what are the ideal characteristics of a t-shirt, and what are you looking for in terms of thermal effusivity? Typically you want a higher thermal effusivity material. So how do you characterize that, and how do you incorporate that into your product supply chain, and define the test requirements for that? So it should be a pretty interesting topic there next week. Now, as Sarah took you through some of the different curated works, you saw a reference to different methods. The modified transient plane source was really in the bulk of the application highlights, and then you saw some really interesting utilities featured there with the transient plane source, which gave you some advanced capabilities for thin films, for anisotropy, and some of these capabilities. There's a great resource that Sarah and her colleagues have authored, a thermal conductivity method selection guide. This is available for download free of charge. It's a great resource to refer to. I think about 50 pages. It covers not just the transient methods, but also steady state methods, and really helps articulate an understanding of which methods work best in which scenarios. As we said at the beginning, there is no silver bullet that covers everything, but this guide does a great job of orienting you to the types of applications which work best with the different methods. Now, just before the start of the recording, I mentioned Sarah is joining us from our new facility that we set up this year in response to the COVID pandemic, where we can't travel and visit you directly. Typically, as part of our consultative process, we would bring in a piece of equipment in, offer an opportunity to demonstrate it on your materials at your facility if this was something that was of interest. That's more difficult to do given the travel restrictions. So we've set up this video facility where we can offer real-time demos. They can be set up very quickly. They can be as short as 20 minutes, or we can do a more in-depth dive. But if you'd be interested in booking a demonstration of what the method looks like on samples that would represent your type of materials, we have a wide selection of materials available to feature, and Arya Hakimian is running those. Sarah's colleague does a great job walking you through a little bit of theory and then diving into the nuts and bolts of what it's like to do from a mechanics perspective. We have different camera angles available, so you can really get a good view overall of what the software is like to operate, what are the dynamics of handling the sample and interfacing it with these different types of sensors. It's a great resource, and I think Rose is going to put up a link here if she hasn't already, just on how to request a video demo. And then the last thing I just wanted to mention before we go to Q&A is that if in looking at this, it piqued your interest and you're wondering, what would one of these systems cost? You're looking at just a quick budgetary estimate for future consideration. There's no commitment whatsoever, and there's no pressure. You won't get any high pressure tactics here, but if you would like just a quick quote, an estimate, we do have a link as well that will be available. You can just put in a little bit of basic information and we'll make a point of turning around a quick quote for you to tweet. So with that said, I want to thank Sarah for doing a great job in curating this materials. I want to thank Rosa Chen and Ana Paula de Castillo as well for helping us with this session, both regional managers here at C-Therm Technologies. And most importantly, you, the audience. We really do very much appreciate you taking the time to join us today. If you're not going to stay online with us for the Q&A session, I wish you a wonderful day, and we'd certainly be happy to pick up these conversations in the future. But thank you all again. Have a wonderful day. I'm going to stop the recording here, Sarah, and we'll move on to the Q&A session.